Good afternoon, advanced algebra students. I hope you're having a great day. I'm looking forward to doing more notes with you. We are continuing on in chapter 3, learning all kinds of interesting things about polynomials. Today, we're going to do lesson 3.5. There's no part A or B, just 3.5. The topic is zeros of polynomial functions. So, we sometimes use so many different vocabulary words in math, but zeros can either mean the roots, the solutions, the x-intercepts, or just speaking in terms of the graph, a zero means where the graph touches the x-axis. So we're going to learn how to find zeros. We're going to learn how having more than one zero can affect a graph, and then ways that we can find zeros when not all of the zeros are real numbers. So in any case, let's kind of dig in here. So at the beginning of chapter 3, we briefly touched on graphing higher order polynomials using information like end behavior. So now we're just going to basically try to fine tune our graphing skills by talking about the zeros. So for example 1, I'm going to show you two different ways. Essentially, we can do this by hand or by calculator. Sometimes for me personally, I prefer doing the work by hand, because in my calculator, sometimes it takes a while to zoom in on the figure and see exactly where the zero is. And to be honest with you, sometimes by the time I input it, resize my window, check my unit scale and all that, I could have just graphed it by hand anyway. But I'm going to show you both ways, and you, of course, can use whichever method you prefer. So for the first example, I have f of x equals 4x cubed plus 4x squared minus 24x. So we can already know some things about this polynomials and behavior just by looking at it here. We know that since it's an odd degree, the ends are going to go in opposite directions. And we also know that since the leading coefficient is positive, that the right-hand side of it is going to go up. But, we can get a little bit more specific than that by factoring it. So let's go ahead and take a 4x out of each term. So then we would have x squared plus x minus 6 left. And then if I want to factor my trinomial here, this is going to be x plus 3 times x minus 2. So you can see that that can be factored really quickly. Doing that, if I set this equal to 0, I can find all three zeros. Remember that typically the number of zeros does correspond to the degree of the polynomial. So if I set 4x equal to 0, I can see that one of my zeros is going to be where x is 0. If I set x plus 3 equal to 0, I can see I'm going to have another 0 at negative 3. And if I set x minus 2 equal to 0, I can see that I have yet another 0 at 2. So we can get a pretty decent graph of this just by plotting our zeros and looking at the end behavior. As I mentioned before, because it is odd degree, the ends are going to go opposite directions. And because the leading coefficient is positive, the right-hand side is going up. And then, I know that in between those zeros, the function is going to have some curves like that. Now, we can plot this on our graphing calculator and get more specific points here, but this is a pretty good representation of the graph just by understanding both the end behavior and the zeros. Now, let's go ahead and take a look at another example that we could factor using synthetic division if we wanted to, but because there's so many zeros in this case, it might be more practical just to do on the calculator. So while we are in class, I will explain to you how to use your calculator to find zeros. There's several different ways you can do it. There's actually a zero feature on your calculator. You can also do a table on your calculator, and you can also just look at the graph on your calculator. But if you plug this into your calculator using any one of those methods, you're going to get zeros at negative 5, negative 1, 2.5, and 4. Again, with the 2.5 here, I would rather see that not so much on a picture, but maybe in a table or on the screen as a number when I ask what the 0 is. So I'm going to go ahead and plot those zeros at -5, -1, 2.5, and 4. I do notice that the ends, because this is a 4th degree or even degree polynomial, the ends are going to go the same direction. I also notice that since the leading coefficient is positive, the right-hand side is going up, but again, because both ends are going the same direction, I know that both ends are going up. And then I can draw, you know, the graph curving through those zeros. So those are kind of brief ways that you can sketch a polynomial function, taking into account both the zeros and the end behavior. Now let's talk about multiple zeros here and the effect they have on a graph. So the multiplicity of a 0 means the number of times its related factor appears. So let's say we have an example, and this will just be a really brief example here, but something along the lines of x minus 1 times x plus 1. Each of these factors only appears once, so that means that they are going to, because that is an odd number, it means that the function is actually going to cross the graph at those numbers. So like if I set x minus 1 equal to 0, I would get a 0 at 1, and if I set x plus 1 equal to 0, I would get a 0 at -1. So all this is telling me is that the function is actually going to cross the graph at those zeros. So if the factor occurs an odd number of times, for instance, 1 time, the function will actually cross the graph where that intercept is. If, however, a factor occurs an even number of times, that is not the case. So for example, let's say our function is x minus 1 quantity squared times x plus 2. Notice that we have 2 zeros here. If I set this one equal to 0, I get a 0 of 1. And if I set this factor equal to 0, I get a 0 of -2. Now, because the factor x plus 2 occurs 1 time, that does mean that the function is going to go through the x-axis at -2. But because this other factor occurs an even number of times, that means that the function is just going to touch it at that spot. So if we were to graph this, for instance, this is what our graph would look like. The function would go through the graph where x is -2, but only touch it where x is 1. All right, so let's kind of talk about some steps of finding zeros. Obviously, we can use our calculator, especially when it comes to finding real zeros. However, it can be a little bit more complicated when we're finding what's called a complex zero, because that's something that does not show up on a graph. Real zeros show up on a graph as being your x-intercept, but an imaginary zero or a complex zero will not show up as touching the x-axis or crossing the x-axis. So we're going to be using 3 steps. The first one is to use our calculator to find a real zero. And then the second step is going to be to use synthetic division. To factor further. And then the third step is going to be, if necessary, use the quadratic formula to find the remaining zeros. Okay, so let's do a few examples. Let's see, I believe this is example 1, 2, 3, 4, 5. So for example 5, we want to find all the real and complex zeros of f of x equals x cubed plus x squared minus 3x minus 6. So if we graph this on a graphing calculator, we can see that the graph crosses the x-axis at 2. It crosses the x-axis at 2. So that means that I know that x minus 2 is a factor. And I know that if I do synthetic division, I will get a remainder of 0 when I put 2 in here. Now, we still want to do the synthetic division because we're going to use this information to find the other factor. I already knew that x minus 2 was a factor and that 2 was a 0, but now this tells me another factor. This tells me that I have x squared plus 3x plus 3. Now, this cannot be factored any further, this second trinomial that we have here, but we can use the quadratic formula if I want to set this equal to 0 to find my remaining zeros. So we already know that 2 is one of the zeros. So the zeros are 2, and now we need to find what we think is going to be 2 more. This is a third degree polynomial, so most likely it does have 3 zeros. When we set x minus 2 equal to 0, we get the 0 we already know about. Then when we set x squared plus 3x plus 3 equal to 0, we can use the quadratic formula to find the other 2. So x is going to be negative b plus or minus the square root of b squared minus 4 times a times c all over 2a. 9 minus 12 is negative 3. Turns out, I guess this is an imaginary solution here. So the negative 1 is going to come out as I. And that gives us our other 2 solutions. All right, let's do another example here. I think we're going to do 2 more examples, just to make sure that you really understand this. So we want to find the x values that are solutions to the equation 2x cubed plus 5x squared minus 3x equals 3x cubed plus 8x squared plus 1. Now, we have a couple different ways that we can do this. We can use these 3 steps here, and this is what I'm going to do. Another possibility, just so you know, would be that we could put both of these graphs into our graphing calculator and see where they intersect. I'm going to solve it using the 3 steps listed above. So I'm going to put everything on one side. I generally like my leading coefficient to be positive if I can, so I'm going to subtract the 2x cubed here. I'm going to subtract the 5x squared, and I'm going to add 3x. So now these all cancel out and I have 0. 3x cubed minus 2x cubed is just x cubed. 8x squared minus 5x squared is 3x squared. And then I have a 3x and a 1. Now, if we do the graph for this on our calculator, we can see that it crosses at negative 1. So if I want to rewrite this, I can write it as x plus 1. Because the graph crosses, let's just write here, the graph crosses the x-axis at negative 1. All right, so I'm going to do synthetic to find some more zeros. Since I have a remainder of 0, I know that this expression is also a factor. This is x squared plus 2x plus 1. And I can continue doing synthetic if I would like. -1 works again. So we'll bring down the 1. Actually, I'll bring these numbers down. 1, 2, 1. All right, so we bring down the 1, -1, -1, 0. This tells me here that I can keep my original factor, that x plus 1 works, and this is also x plus 1. So all of the zeros basically are just the 1. The 1, 0 is just x equals -1. Typically, when we have a third degree polynomial function, we are going to have 3 zeros, but in this case, the only 0 that works for this graph is -1. Now, we can do something very similar to this when we have an inequality. It's the same process. We're just going to look more at the graph to get our final answer. So this is our last example here. I believe this is example 8. Could be wrong about that. So let's go ahead and ask ourselves, what x values are solutions to the inequality x cubed plus 4x squared minus 4x minus 16 is greater than 0? So first, what I want to do is find the zeros. I can see that there is a root at -1. So let's see here. Oops, no. It looks like, sorry, I was looking at a different problem. It looks like that there is a 0 at -2, +2, and -4. This one actually is fairly easy to factor if I just want to use factoring by grouping. So I'm going to do x squared times x plus 4 minus 4 times x plus 4. This becomes x squared minus 4 times x plus 4. I could have looked for a 0 on my calculator and then used synthetic, but this was super easy to factor using factoring by grouping, so I just did that. But if we wanted to plot these zeros, this would be a 0 of -2, this would be a 0 of +2, and that would be a 0 of -4. I know from my end behavior, the ends are going to go opposite directions because it's odd degree, and also that the right-hand side is going to go up. Now the question is asking, when is the function positive? So if we look at our graph here, the function is positive in this part of the graph here, as well as this part here. So f of x is positive, or f of x is greater than 0, when x is between -4 and -2, or when x is greater than +2. Again, another fairly long notes. I super appreciate you guys hanging in there. I do think it's going to really help you in class to watch this. Thank you. Bye.